Hi, everybody. I'm so happy to present our ORAI speaker today, my great collaborator and friend for many, many years, Serdar Kadioglu. He's actually a group vice president in the AI Center of Fidelity Investments, but also has stayed close to research and academia as an adjunct associate professor in computer science at Brown University. Serdar has worked also at other industry before Fidelity in Oracle and Adobe, and has led multi-sector partnerships with NVIDIA and others. He does a lot of work at the intersection of machine learning and combinatorial optimization, and he's going to be telling about some of it today, but he also has recently really also stepped into large language models and constraint reasoning. So without further ado, I'm really looking forward to hearing what you have for us. Thank you so much.
Thank you very much, Vistra. It's a pleasure to be here, and I appreciate your kind invitation. And thank you, everyone, for joining us. I'm sure you're all aware we're living in interesting times. Foundational models emerged as the communication medium with machines. Remarkable results in natural language processing, in computer vision. And if you're coming from an optimization background, you might be wondering, what does that mean for us in the field of optimization? And that question might be quite obvious and quite natural. What might not be as obvious is what would the road to that end state would look like, and what would the building blocks to enable something similar in optimization? And that's what exactly I'm going to talk about today. My name is Serdar. I'm helping Fidelity to build these AI systems and optimization systems for real-world products, and in parallel, continue to serve the academia as well. And in particular, I want to talk about Forge, one of our recent work in this domain, foundational optimization representations using graph embeddings. And I'll share what that means and some experience along the way that we learned while building these systems. So let's just set the stage in two ways. One is, where does this talk fit in the big picture of academia, and where does it fit within Fidelity AI Center, so that you have some mental picture about it. If I look at AI, we can classify it broadly into learning and reasoning systems. And I use these terms quite loosely, maybe call it data science on one hand, and I lump everything from machine learning, deep learning, LLMs, vision, NLP in that bucket. And maybe the reasoning systems, decision science, if you will, operations research, SMT solving, SAT solving, constraint programming, I lump that on the other end. These are also referred to as system one and system two thinking. Predictive models that tries to learn statistical patterns from historical data sets. They're pretty good working with unstructured information. And prescriptive models, maybe constraint models, optimization models that are very good in precise logic and reasoning, and can even give you provably optimal results or guarantees if everything is deterministic, and perfect for structured domains. This talk is going to be at the intersection where I'm trying to use some techniques from the learning community to help us in the optimization space. If you're curious about maybe a historical evolution of AI paradigms, I'll drop a note here for our triple AI, educational AI videos on the evolution of AI paradigms from classical AI to modern AI and generative AI, and point out there. And where does it fit within Fidelity Investments? So here are the strategic pillars, the way we think about AI as part of the AI Center. It revolves around these 5 pillars. We want to learn from offline data sets, whether it's structured, unstructured, or semi-structured. We want to learn from these systems as they're up and running. We want to learn from online feedback. We want to use AI for decision-making, especially large-scale resource allocation and management problems. More so recently, we want to look into co-pilot experiences, automated assistance in several different domains, and maybe as a horizontal capability in responsible AI to think about the implications, the fairness, the bias, and general evolution of these systems across the board. Within each, you would see some of the recent work accompanied by their open source software as well. And I'll drop another note here if you want to learn a bit more. What does that look like, and what's the AI strategy behind this to establish this in the enterprise ecosystems, and how to combine all this together into modular frameworks and contribute to open source. I'll point out to the recent article at AI Magazine. So that is what it looks like from the big picture and from Fidelity's perspective. But the specific topic of today, I'll be talking about mixed integer programming. Might be already familiar with minimizing some cost or maximizing some value subject to constraints where your decision variables could be continuous or integer. I'm going to need two definitions for the purpose of this talk. The LP relaxation, which is where you take the continuous relaxation of your integer variables. That gives you a nice bounding procedure if you're to do, let's say, branch and bound. And then the gap between the LP relaxation and the optimum integer value. That's the LP relaxations and other contributions. So we're going to look at the integrality gap as well in these problems. So that's essentially what this talk is centered around, mixed integer programming. And learning and reasoning, combining their hybrids for optimization is definitely not new. There's a lot of work that happened in this domain. I'll mention the existing, I'd say, more classical machine learning and operations research intersections. So people have done a lot of variable guidance, search guidance, branching prediction, algorithm portfolios, node selection, cut selection, just to name a few. And there's some work from our group in this line as well. I'll mention Balance in particular because that's our collaboration with Bistra, which is an online meta solver that tries to learn on the instance at hand to configure these MIP solvers, underlying MIP solvers to do that. What's also emerging is the maybe more recent in NLP plus OR combinations, where you're trying to do these automated model formulations, maybe modeling assistance, natural language interfaces, maybe explanations using some of this language technology. I'll mention a few of our work here and maybe pick up the global agentic framework, again with Bistra and her group here at USC, where we're trying to do these agentic decompositions, but focusing on global constraints. But there is a lot more than I can fit in one slide. That's quite rich wealth of literature in there. That's all good and nice, but all these learning approaches to optimization has some practical limitations. Number one, training them is not easy. You have to be very careful in creating your data sets on finding the right distributions and representative instances so that you can train these systems and learn from that. Let's say you put that effort and you train those systems, you'll still be stuck with some limited generalization. Extending them to new domains, new problems, new sizes, new variants will always be an obstacle. And somewhat ironically, most of this learning is supervised. So you need to have a solver at hand, first of all, to train these systems. And you're trying to speed up the solvers in the first place. So you can't really train this thing on anything that the solvers can't solve. So I find it quite ironic that this circular solver dependency in training these systems kind of a deal breaker for me. And that's been stuck with me for a long time and it bugs me. And I'm like, we should be doing something about this. So these are some of the main problems with the learning systems. And the bigger picture, the vision here is you look at the remarkable success of foundational models in both large language models and large vision models. And we've come a long way with our understanding of the semantic representations for text, image, audio, video. And this is done through unsupervised or self-supervised training. And that's really, really nice. Like I really like that. I'm very jealous of that coming from an optimization domain. The key question is, how can we enable something similar? What does a foundational model would look like? Can we leverage existing MIP instances? How do we pre-train this thing? Does it even work? That's sort of the main central question here. And what do I mean by foundational is a single pre-trained model that I can pick up off the shelf. I can use it across different problem domains, across varying sizes. And I don't need to spend this time to retrain again. The pretty good example is the king minus men plus woman equals the embedding of the queen example from the NLP domain. And that's quite nice. It just tells you that there's something semantically that you can capture in this latent space. And if you have something like this, it's very powerful because you don't need to know, for instance, the capital of Turkey is Ankara. Istanbul will be the most common incorrect answer. But if you know the relationship between, let's say, Spain and Madrid, you can apply for it. And now you have quite a nice retrieval system where you can do question answering. So these semantic representations are very powerful, and we want to enable that within optimization. And here's a photo of Bistra and I in Darstool. And this was actually, there was an entire seminar where we discussed this whole thing for like a week on data-driven combinatorial optimization. So that was a while back, and since then, this problem kept bugging me, and we've been trying at it and failing it many times. But I think we have a partial answer right now that I'd like to share with you. And this direction is eminent given the growing success of learning-based methods so far. I'll mention a few. For instance, Zhu et al. Shows that you can actually build these meta-learning frameworks, and they can work on different problem variants, except that they're doing it for a specific domain, vehicle routing in this case. But it's very nice. You can actually do quite a bit of a generalization within that domain. Another work from, a lot of work coming from Bistra's group here, where you can actually say that, look, I can do this for multiple tasks using a shared backbone network. I can do both backdoor prediction and solver configuration, completely different tasks. And I can do that. I can extend this into multitask, not just multivariants. Or even, some recent LLM-based approaches where you can create these, diverse MIP instances to actually enable maybe more training, but that has some, again, dependency on having a solver attend in the first place, so that you have to run some labels. So all in all, today there exists no general purpose MIP embedding model out there. And that is the gap we're trying to address. The existing work either can work in multiple variants, but is very problem specific, like vehicle routing, or you could do this for across problems, scales and sizes, but limited to a certain problematic task. Or you have this supervision that we're trying to get rid of, that we don't depend on the solvers. And that's essentially the motivation behind Forge. We would like to build a pre-training framework that learns structural representations across a diverse set of MIP instances. And we want to be able to do that at the instance level. Just like I give you a word and you give me a word embedding, I want to give you a MIP instance and you give me a MIP representation. And I want to do that in an unsupervised manner. I don't want to depend on solvers in order to do that. And I don't want to have access to their solution or anything either. How are we going to achieve that? There will be two inspirations, one coming from NLP, one coming from computer vision. From NLP, we will adopt the concept of a vocabulary. So we'll say, okay, there will be a vocabulary that represents this latent space of optimization problems. And then we will use this technique called vector quantization coming from computer vision, where we're trying to preserve that global information of what that instance means within that latent space. And both are pretty well established within their internal communities, but what we're trying to do here is to, again, to bridge that learning to reasoning sides of the coin and use these techniques from NLP and vision for our purposes in optimization. Okay, so what you're going to see in the remainder of this talk, what are our contributions? I'll show you how we can build this foundational model. That model will give you local and global structure. So I'll show you what that looks like. But at the end of it, you will get a representation for the overall instance. You'll get a representation for the variables individually if you want. You get a representation for constraints within the problem if you want. I'm going to show you that it generalizes quite well in an unsupervised setting. I'll use some clustering examples. On unseen, untrained data sets, it does a pretty good job out of the box. And then I'll extend that to supervised adaptability, where I'm going to take that same pre-trained model. I'll pair it with some cheap labeling strategy to do a bit of fine-tuning, but not too much, and then show that it works quite well in different tasks. And I'm going to take those methods and integrate them into optimization solvers to see, does it make the solvers better? And I'm going to take that and augment existing learning methods. Can I take this off the shelf and make what exists out there better out of the box as well? So that's going to be the rest of the talk, essentially. Let's start with what does this look like? What's the magic behind? And that is the entire talk in one slide. You don't have to understand it right now. I'm going to walk component by component. But essentially, the high-level idea is that we're going to use this thing called vector-quantized graph autoencoder, and we're going to use that at the end to reconstruct a representation that we can get out of the box on the instances, so that we move away from this solver dependency. And the architecture from left to right will have a bipartite graph on the left, that will go into a graph neural network. And then comes the middle part, the magic, the vector quantization, and then the reconstruction, and then the loss function to learn from what we're reconstructing. Okay, so let's jump into each little component one by one. We start with the MIP instance to bipartite representation. This is pretty well established, so nothing that we didn't know here. We'll take the variables and the constraints on one side, variables on the other. An edge between them is the scope of that constraint, if the variable is exhibited in that constraint or not. And we're going to attach every node with some node features, and it's very, very simple node features. So I'm going to use 4 features for constraints. That's essentially the sense, the less or equal or greater or equal or equality, and the right-hand side value. And then for variables, I'll use 6 features. Is the binary, is the integer, is the continuous variable, what's its upper bound, lower bound, and what's its coefficient in the objective. So, the nice thing about this is notice that I'm not trying to depend on any solver level information. So the original work that does this bipartite representation, they would actually run the solver a little bit and then learn something about these variables and constraints and put them as part of their node features. I don't want that. I just want to read what I can read from the instance out of the box. 4 features, 6 features, a vector of 10, padded with zeros, depending on the type of the constraint, the type of the node. So that's what we start with. I took the instance. Now I have the bipartite graph and a vector of size 10 for every node. What do I do after that? I send this into a graph neural network. We'll use Graph Sage in this case. And what it is going to do is it's going to take these vectors, static input vectors of size 10, and it will put them into some GNN embedding of some dimension D. Okay, now you're moving from this out-of-the-box instance features to a latent representation. Again, this is pretty, this is done quite often in the literature. There is a problem with this, which we need to solve. And that problem is, notice how the GNN embeddings is quite nice. That gives you a capturing of the nodes, whether it's a variable or a constraint. And that's quite nice. You can learn a lot about these variables and constraints if you want. But it doesn't tell you much about the instance. So there's something called locality bias. It's pretty well studied in the domain as well, that you capture this local information, but if you were to take, let's say, the mean pooling of these things and say that's my instance, that actually lose a lot of information because of the over-smoothing. And that is something we have to deal with. The locality challenge is one of the main problems here. Okay, and here's where the magic comes in. So we're going to say that let's assume there is a code book of size k with k discrete codes, and the idea is that will serve as the vocabulary to represent the optimization space, very similar to language models. And this code book exists not just for one instance, but it exists across a domain of instances and different difficulties. Pretty well used in the computer vision community, called structure-aware graph tokenizers. But the point that it does is, it helps us circumvent this over-smoothing issue of the GNN mean pooling of the embeddings. So I start with the bipartite instance. I throw it into a GNN to get an embedding. Now I imagine there will be some code words, the vocabulary to represent this thing. And then what I'm going to do next is to assign each code book with a code word. And this code word is actually a D-dimensional embedding itself. And I'm going to say that every node in that bipartite graph that has a GNN embedding will be assigned to a discrete code. Okay? So there's an alignment on the dimensions here. The code words also are of dimension D. And each code book will be mapped into a code word. So one of the nodes will get a code, let's say code number 1, and the code number 1 has a latent representation of size D vector that corresponds to the code word of that code book. I hope that makes sense. So that's how vector quantization works. Again, the dimensions are in alignment here. And then what I can do is that I can say, okay, if I have this code word for these nodes, which could be variable nodes or constraint nodes, cannot I reconstruct the bipartite graph that I started with in the first place? And that is where the unsupervised learning is going to kick in. We're going to, like, we basically took the instance, we encoded it, and now I need some decoders to put it back to what I learned from the instance in the first place. All right, so I'm gonna have two decoders. One is to decode the nodes. What does that node look like by just looking at the code word? And then edge decoder, whether there's an edge between the nodes or not. So, you know, the reconstruction process is to just replicate back the nodes and the edges of what I started with. And the main point here is that I don't need a solver to do this. I can just do this over instances, so I can do unsupervised learning. Okay, back to the picture again. I hope that makes a bit more sense now. I start with the instance. I said that there is a code book of size K that represents this MIP space. Notice that this is across multiple instances, so I can send many, many instances and learn this reconstruction loss. Let me maybe say a few words about the loss function here. So what are we going to train this with? The loss function will have essentially the edge reconstruction and the node reconstruction that I'm trying to replicate back, as well as something about this quantization to make sure that the quantization is working correctly. There's two components of it, the codebook loss and the commitment loss. The codebook loss is you take these node embeddings and treat them as static, and you move the code verse close to them so they are capturing this instance better. And then the commitment loss is you made sure that these nodes commit to their closest codebook. So that's kind of the opposite side of that equation. I'll skip you the formulas so you could look into the paper, but let me give you the intuition behind the loss function. The main intuition is you can think of it as a clustering. Like I think it's very much like K-means, where you have some data, some samples, and you're trying to cluster that. You want to make sure the clusters are perfectly capturing the whole space. The nice thing is, the clusters are essentially the code books here. So you want to make sure the code books are covering your latent representation. So there's the codebook loss of how closely you're doing this, but also the instances can move. Notice the instance, what I call in a clustering sense, the instances here are the node representations, and that's not fixed either. So you're kind of doing a clustering with some centroids, but at the same time, the other samples can also move around. So one of them is the commitment loss, the other one is the loss coming from the codebooks themselves. And then you're trying to balance this loss with the reconstructions. Okay, so that's the intuition behind the loss function. Let's say we do this, what does that give us? So what are we going to have at the end of this process? It's going to give us multi-level representations. Notice that for every node, whether it's a constraint node or a variable node, I have assigned a code book. And that code book has a code word, which is a latent representation. So I'm going to get local representation just as before. So I'm going to have a vector representation for every variable and every constraint. And then what we're going to do is what we want is an instance level embedding. And I'll have an example there. If you have, let's say, code 1, and its frequency for one instance, it shows up 3 times, and the assignments, I'm going to call it the code 1 is number 3. So I'm going to look at the distribution of these codes in that particular instance. And in this case, I'll have, let's say, five codes, and code number 1 is used 3 times, code number 2 is used 2 times, and I'll have this vector 3, 2, 3, et cetera, et cetera. So I'm going to get this embedding structure from the frequency distribution of these codes for that particular instance. Okay. Any questions so far? This may be a good place. Yes, please.
Just for clarification, you're assuming the number of variables and constraints are way higher than the number of codes that you have?
That is a good question. I'm not making that assumption. We have some ablation studies on how these code sizes affect what representation you're going to get. For the particular case here, the code size is 5,000. And I might have instances there that may not have 5,000 variables or constraints.
The reason I ask is because you're looking at this frequency. If the number of codes are much smaller, that makes sense. But if it's not, then you might just get the frequency of 0 or 1.
Correct. So if you have like 1 million codes, you will have this trouble of a lot of codes not being used, and that's a pretty well known artifact of the code book, the vocabulary itself. So there's a bit of a sweet spot there. And what people found is that there's a bit of a diminishing returns. There's a nice representation, after which you wouldn't see any improvement in general downstream tasks. In this case, it's going to be 5K, and that's, we also see that, you know, not enough code books doesn't capture too many, lots of sparsity. So there's a, so that makes a lot of sense. Other questions? Yes, please.
Did you try just doing sort of an encoding, decoding layer without the code book, so just on the graph embeddings, and then just have a loss based on how close the representations are at the end? Like,
Correct.
did that just not work at all?
Yes, we did. I actually will show you an ablation on that in a second. And that was the balancing act between the reconstruction and the decoding part. So if maybe one side is there or not, you will get different results. In the case of Forge, it's 50-50. So we learn 50% from one side, 50% the other side. I have an ablation on that in a second. Yes, Mr.
So when you have the embeddings, it doesn't, by that time, it doesn't know the edges. It has to actually, in the reconstruction, guess which variable belongs to which constraint.
Correct.
But in the beginning, when you input with the bipartite graph, do you actually have the coefficients of the variables in the constraint? You have edge features?
Yes, we have. Yeah, good question.
And do you reconstruct that as well?
Yes, we do reconstruct that. So it's not just, maybe I did mention that and didn't really talk about it. It's both the structure and the features, and also on the edges. Yes, on the edge features as well. That's a very precise question. I'm going to double check that in the paper next time. Okay, so that's the methodology. If you're with me so far, what we're going to get out of it is an instance level representation. The obvious question is, does it work? I'm going to do some unsupervised exercises in the next couple of slides. Here's what the setup looks like. We're going to take these Forge embeddings, and we're trying to cluster unseen instances and see, okay, does this codebook space capture anything? What I'm going to do is I'm going to train on MIBLIB instances. It's a very standard benchmark data set. And then I'm going to test on distributional MIBLIB. So I'm not training on dMIBLIB, I'm training on MIBLIB and testing on dMIBLIB. The reason I'm doing it, you could do this both ways, it doesn't really matter. The reason I'm doing it, MIBLIB is just a kitchen sink of instances. There's lots of different instances in there. And dMIBLIB is super nice. And it tells you, these instances come from this domain and this difficulty and so on. So I can use that as my ground truth to actually check, did I get it right at the end? So that's the only reason I'm doing it in this direction. But in principle, both should work. We'll do some clustering, and then we'll look at NMI on, how good I'm gonna get back these 21 different combinations of problem domain / difficulty pairs. Little details on the training. I'm going to train this on 600 instances from MIBLIB. For every instance, I'm going to drop 5% and 10% of the constraints and call them as 2 other additional instances. So I'll augment it. In total, I'm going to end up with 1,800 MIB instances with training. And as far as the parameters go, the codebook K equals 5,000 is a good representation. I don't have it on the slides, but there's an ablation of what that means. And then I have 1,024 dimension embeddings. The dMIBLIB, thanks to, again, Bistra's group, Waymin, who contributed this very nice data set to the community, involves lots of set cover, independent sets, combinatorial auctions, vertex cover, item placement, and so on. So it's a quite nice mix of data set, but it tells you the distributions behind these instances, and they have different difficulties, easy, medium, hard, extra hard, and so on. Okay, baseline comparisons. I'm going to do the mean readout. So to your point, if you don't have, the loss coming from the reconstruction and just look at your GNN embeddings and to make sure you get the best embeddings and take a mean out of that to represent the entire instance, this is what you're going to have. So you can think of this is what existed before we did this work. And it's a good ablation because Forge itself uses the same MIB embeddings to do the reconstruction. So this is mean readout. If you have those 10 input features on every node, like I said, you can do a 2-hop label propagation and see, what can you learn from that, and that's another comparison. And of course, we'll look at the distribution of these discrete codes at the instance level from the Forge side and see what that looks like. And this is what it looks like if you do this. The mean readout on the left is pretty much arbitrary, like there's no structure whatsoever. Even though these GNN embeddings are pretty good at the local level, when you take the mean readout, over smoothing just loses everything. So you end up with like pretty much a random representation. And that is the locality bias problem that I talked about. If you do label propagation, it gets a lot better. I'm showing you the NMI results. NMI results, 100% means that you get back every 21 class correctly if you do this clustering. And then the numbers go quite up when you do the label propagation. And the best achieved with Forge. I'm not sure if it's very visible, but if you look at these those problems, you actually see they're not just clustered, but also the gradient of easy, medium, hard, extra hard is also there. You zoom in and look at the legends and so on. So again, Forge has not seen any of these instances. It's just trained on MIPLib, and it can cluster pretty cleanly the instances in the distributional MIPLib. So I started with the king minus man plus woman, the famous example from NLP. And if you just look at these problems, we have set cover and vertex cover, which are like covering problems. And then you have the bin packing and the independent set, which are basically packing problems. And there's a nice duality between the two. If you take the minimum vertex cover and the size of that plus the size of the maximum independent set, you get back the number of nodes in your graph. So there's clearly a relationship here. And we wanted to do something fun, like, if you can do vector arithmetics in NLP on these words, can't we do something similar in optimization, or what would it look like? And that's what we kind of played around with, doing a bit of vector arithmetics in this latent space because it nicely clusters. So I'm going to show you one of them. What happens if I take vertex cover instances, try to get rid of that cover dimension, and add a packing dimension? Do I get back independent set? Because that's what the theory, that's the relationship between these graph problems. It's a bit of a stretch analogy. It's a bit more fun than anything else, because we don't have a single king instance in optimization. There's no vertex cover. It's not one instance. So what we're going to do is we're going to fix the graph size. We're going to say, okay, we're going to look at a bunch of them, 50 within each problem, and we're going to look at comparable graph sizes. We'll fix the graph size to 1,000 vertices, and we're going to control their difficulty, so they're all solvable within 60 seconds using the Groby solver. So that's kind of like I'm trying to narrow down the setup. And then we're going to look at the mean embeddings of all vertex cover instances, the mean embeddings of the set cover instances. We're going to deduct the mean of the set cover from vertex cover to get rid of the cover dimension, add the packing dimension, and we're going to test if we get independent set back. This is what the space looks like. If you just cluster these, you have the set cover, the reds, the one in purple, the bin packing. The one I'm trying to update is the vertex cover in purple here. I'm going to get rid of the set cover dimension, add the packing dimension, and I'm going to see if it's close to what's in yellow, the independent set. And if you do that arithmetic, this is what happens. So all of a sudden, you started with vertex cover instances, you did some vector arithmetic in this latent space, and you end up with MIP representations that's pretty much independent set, which is what you would expect from the theory. So this is more fun. So I played around a lot just doing this in many, many directions on different problems, but it gives some intuition that there is actually something that we're capturing in this latent space. Okay, that's enough unsupervised fun stuff. I want to actually do some more interesting test cases. Let's move on to the supervised case, where we can now take this pre-trained model, fine-tune it on some interesting task, and see how it works when I integrate it into the solvers and what it means when I compare it with other learning approaches or augment them. Before I jump in, any questions on the clustering side of the world? Yes.
Again, a clarification. So for each one of these, you end up with a bunch of embeddings for each node, right? So you don't have a single embedding for the—
Correct. So I take every instance of the, let's say, the vertex cover, and from each one of them, I deduct the mean of the set cover instances.
For each node?
Yes.
Oh, I see. Okay.
That's why every dot becomes still a dot. They just moved in the directions. But the directions are apparently meaningful that when I moved them, they just ended up where independent set was, which is a bit—
I thought you were doing the arithmetic on the instance embedding, that code book histogram.
Correct, on the instance embedding, but then to get a direction of a cover. What's the cover direction? It's the mean of the instances of the set cover.
But you're not taking the mean of the nodes. You're taking the mean of that histogram.
Correct, of the instances.
The arithmetic is on the instance encoding, which is that histogram of code
Correct.
elements.
Correct. But I think you're both saying the same thing. Or at least I misunderstood something.
He said node, averaging the nodes in each instance.
The node embedding, but I think I'm.
Okay. As long as you're happy, I'm happy. I think we're getting confused with the nodes in the bipartite graph and the nodes as in instances in the clusters. But okay. All right, let's move on to supervision. I'll tell you a little bit of the experimental setup. So let's shift to see how Forge can help improve MIP solving. That's what we started with. I want tasks that are that is important for MIP solving in the first place. I want them to be relevant in the literature so that I can compare with something, so there's some fair comparison. I want them to be very different from each other so that I can test for generality. And I want them to be solver agnostic. I don't want to depend on a solver implementation or how they do the branch and boundary and so on. So that's how we go about it. And in all experiments, I'm going to use the same pre-trained Forge model that I showed you how I trained with the reconstruction laws across problems, across sizes, across different tasks. And the two tasks that I'm going to look at is the integrality gap prediction. So I started with that definition in the beginning. Given a MIP instance, I want to just be able to predict what's your integrality gap without actually solving for integrality gap. And within an instance, I want to know something about the variable assignments so that I can guide the solver using hints to say, okay, this is probably a inclusion variable, this is probably a zero exclusion variable, and so on. Any questions on the tasks? These are pretty standard in MIP solving. And the main idea, the way it's going to look like is this. So I'll have the whole setup that I showed you before, where I'm going to end up with these code words for my variables and constraints. I'm going to add these prediction heads that's going to do the integrality gap prediction or the search guidance prediction on the variables. And I'm going to fine tune the same pre-trained model. And I want this fine-tuning labels to be labeled with a cheap labeling strategy. So I don't want to solve an entire instance to be able to train this thing. And the analogy is like, in NLP, if you were to do some entity extraction, you would start with your famous sentence transform, you would encode it. And if you're coming from a finance domain or a healthcare domain, you would have a small created data set of your very specific domain applications, and you would train that on this small data set on this fine-tuned examples. So that's very similar. I want to be able to take the pre-trained model, fine-tune it on small set of instances that are cheaply labeled. So that's the philosophy behind the second set of experiments. Nothing changes in the training setup, except that I now don't need to train them separately. I took the MIPLib and the distributional MIPLib and train on all of that, but the same architecture, same everything. If you're curious, I'm going to end up with a model with 3.25 million parameters in it. That's what the Forge model currently contains. Let's start with the task number one, predicting the integrality gap. The idea is to do that without solving to optimality. And I was wondering when we first started doing this, isn't there a magic constant? Can't I just say, just take the LP, make it 10% worse, and pretend that was your integrality gap? Like, does it, like, how far would it go from the LP at the root node? And we then looked at the distribution of where that lies. So these are different classes of problem domains. And I'm telling you the distribution of the integrality gap across them. And turns out it could be 5% away. It could be 95% away. So you really don't know for any given instance. You can't just say that it's 10% all the time. So this is indeed a learning problem. And if you do this incorrectly, you might invalidate the instance. You might actually end up with an erroneous result. So you can't really make this incorrect. Otherwise, the solver will say there's no solution. So this is, that's kind of the difficulty behind this problem. I'm going to train on a very small data set, like 50 instances within auction set cover independent set on easy, medium, hard. And then I'm going to collect the label as in I'll run the solver a little bit, 2 minutes, and I'll pretend that is what I have as the integrality label. So I don't need to wait until the optimality. And based on that label, I'm going to add this integrality gap prediction head. It's a regression problem. I'll look at the error in my in my regression task, and will train this thing to get the good prediction head on these 450 labels. And on the left side, I'm going to use start with the pre-trained model. If I can do this, the test setup will be, I'm going to test this on very hard instances on these different problems that was not part of my training. And also vertex cover, which is not part of the training at all. Not even easy, not even medium, not at all. And I'm going to then, if I can predict the gap, I can just add a constraint to the solver to speed up things. If I know that the AP relaxation will not be, will be that far from the optimality, I can then integrate a pseudo cut. And it's a pseudo cut because I don't have proof that this is correct. It's just a prediction, so it's a pseudo cut generation. Okay, so 2 tests. Does the prediction work? Does it make the solver better? Does it work? So here's how far off the errors. The lower the better. On these different problems, the errors range anywhere from 12 to 20%. As an ablation, if you don't use the pre-trained model, in all cases, the errors would jump about 30, 35%. So there's definitely something that's coming from the pre-training. And then if you run the Groby solver, which is the red line at the top, and the same setup on every class, on every instance, plus the predicted gap as a pseudo cut, that's the green line. The lower the better, it's closing the primal gap up to 85%. And these are on very hard instances that I didn't train, and even on MVC that I haven't seen in training at all. Okay, so what do people do for this task in the field? I'm going to compare with Lee et al. And what they're doing is they have this really nice way to generate instances, and because they have it, they now generate massive data sets and train on them, problem by problem, problem specific, and do the same task of predicting the gap. And their error rate is about 20%. I test on their test data set that I've never seen before or never trained with just the pre-training that I showed you plus the prediction had 18%. So quite competitive out of the box with no additional training. And let me jump onto this task 2, guiding the search. The idea, again, I used the global representations, the node representations, and in this next task, I want to test the local representations, specifically the variable representations. And I want to learn some hints about these variables so that I can guide my search. How are we going to do this training and the labeling? I'm going to find some feasible solutions by running Groby for 5 minutes. And then if the variables shows up as positive, as in they're included in the solution in any one of the 5, I'll call them my positive variables. And if they never show up positively, I'll call them my negative variables. And then if a variable shows up in the same number of solutions, I'll call them as the anchor positive pairs. So I'm going to have this triplet loss on this positive, negative, and anchor pairs. Yes.
So variable fitting in a solution, I think this is just because you're talking about binary problems.
Mm-hmm.
So every variable appears in every solution, it just has a value.
Yes, correct. As in, it shows up in the assignment with a 0 or 1. Is it included or is it excluded from the solution and the full assignment? And I run it and get first 5 feasible solutions, and I say, you never show up positively in any of the 5. You've never included in any of the 5 solutions, I'll call you a negative variable. So the point is to come up with a cheap labeling technology. I don't need to solve this to your optimality. I just need to get like the first 5 solutions and learn my positive negative pairs. And then, the tricky part of the triplet loss is you need to find some negatives that are actually meaningful. It's very easy to find any negative, but because we have this embedding space, I'm going to use my unsupervised forge embeddings to look at the variable embeddings of those anchors and going to pick something that is negative that's very, very close. So it will look almost the same to a positive, but it will not, it will be negative. So that's a tricky, that's a pretty subtle detail of how the pre-training is actually helping me to come up with these meaningful positive and negative pairs. And I'm gonna train this with the the cross entropy loss? Did you get the variable assignment correct while making sure that the positive n anchors are close and the negative is a margin away from them? I'm gonna so what do? You know, if you have these labels and train it, at the test time, I'm gonna run Groby like 1 second and it will find a solution and that will become my anchor. And in that anchor, I'll look at, okay, what variables are included, what variables are not included. The variables that are included in that first solution and is in the top decile of my variable predictions, I'll call them for inclusion. I'll hint to the solver to include them in the solution. And the ones that is close, what is in the bottom decile of my predictor says these are negatives, I'll tell the solver a negative hint. And if you do that, you know, the green line is again the Groby with these variable hints, and the red line is Groby default. You improve the primal gap about 40%, 35% speed up across all problems, all difficulties, all sizes. And then, you know, this is the last experiment I'll show. Look at the same task in the field. And we said, okay, why don't we just like, if these pre-trained embeddings are good, can I just take them out of the box and just add it on top of, you know, some other learning method? Does it make them better if I just augment them? So what we're going to do is we're going to take PS Groby and we're going to just add forge embeddings as is on top of their variable and node embeddings. We have to do a bit of a PCA because I have 1,000 dimensions. Their architecture is smaller, so I need to do a PCA before I can do the addition. But that's the idea, and then we'll look at the common subset of problems that they reported on and we reported on. The light blue is their methodology, the PS Groby, and I didn't do anything. I just take what they're doing and just added my embeddings on top and rerun everything again. And on these two problems that we have common instances, combinatorial auctions becomes 40% better, independence set becomes 50% better. So these pre-trained embeddings, you can do clustering, you can add it to your solver, or you can add it to your learning methodology. That's essentially the gist of what I've been trying to show. Let's wrap up with some limitations. So what is, you know, what are some immediate limits? Number one, we really didn't do much about training this model. It's a very, very compact, small model. Like I've been talking about vision and language, and this is not even comparable. It's just like 3 million parameters tuned on 2,000 instances. Right now, we have some work underway, any MIP instance under the sun that we can get our hands on, like nothing stops us to just use this thing to train the whole architecture again. So this was a bit more methodological so far, but nothing stops us from blasting this, which is what we're doing. I think this is super interesting. There is something about those codes. Clearly, like the vector arithmetics in this space blow my mind because I'm like, oh, okay, I can now talk to these things. But what do they mean? Like, what is code number one's meaning? I think there's a lot of interpretability that we can learn from that. Some initial intuition that we are seeing is maybe one code is depicting maybe a clique of variables. And it understands that it has a clique of variables. And then it doesn't matter what problem it is, as long as it sees that graph structure there, that code is actually denoting that. But it's a bit hand-wavy so far. Like I think there's a lot of interpretability in understanding what these dimensions are. And all the experiments I showed you was one shot. I had the solver, I predicted the gap, add a cut, call it a day, and run the solver. I run the solver, added a hint, call it a day. But I have this thing running now. I can do these cuts and integrations many, many times during search all the time, and closer augmentation. It doesn't have to be up in the root node once and for all. And even then it helps quite a lot. I don't know what it would do if I do this multiple times. So where do we go from here? I think there's a lot of other downstream tasks, node selection, variable select, cut selection, portfolio construction. So we can just see where these pre-trained models do help. And I don't think the methodology, the framework is specific to MIPS in the first place. Why can't we just use the same for constraint satisfaction problems or Boolean satisfiability? And I don't think it's specific to branch and bound either. We can also use this for heuristics or meta-heuristics. So there's a lot of work that can happen on top of this. I think we just barely scratched the surface. And one final word on the open source. So all these data sets, how we're training them, the pre-trained models, so that you don't have to do this on your own and you can just download, just like you would download your favorite text embedding from Hugging Face and get your MIP embeddings out of the box. I'll build some optimization as a service on top so that you can give me a MIP, I can give you a prediction. Give me a MIP, I can give you an embedding, and essentially build up this ecosystem and structure around being able to depend in each other's work and leverage what has been done before, as in many learning domains to benefit and get the network effect out of everyone's research. That's where I'm going to stop. So I showed you an unsupervised method for learning MIP embeddings at the local and global level. There is some very promising results, and maybe it will be applicable in your own work or in other domains too. And I'll pause there. Thank you.
So much for a wonderful seminar. We have time for questions, so.
Yes, please.
When you're looking at your loss function to see how well you reconstructed the problem, is there any notion of reconstructing a problem that numerically looks different from the initial problem, but is semantically equivalent? And I guess the follow-up to that is, does it matter if you fit without that?
I do not know, to be honest. Like, I do not know what it means. It's semantically similar, but not in the embedding space, because the vector arithmetics almost hints me in the other direction, that there is actually something in the space itself that they should be close if they are semantically similar. So that kind of goes a bit against of what I would intuitively believe in. But again, I mean, there's so many more ablations and different loss functions that we could try on top of this that I don't think we have covered much of the possibilities there. We didn't even tune how do you balance the reconstruction versus the commitment loss. It's just 50-50 so far, and I didn't want it to play around. I just want to see as a methodology, does it give you anything? So yeah, I do not know, but I would be surprised if they mean the same thing, but the embedding space is distant.
So I got stuck with the part that you have this 10-dimensional vector for each vertex, and the 4, like in the case of variables, I think 4 of them are wasted in the constraint, 6 of them are.
I forgot which one is which, but one has 4 features and one has 6,
Right.
and then we say everything has 10 and just pad them depending on the type.
So I'm thinking, and then you do convolution on the graph, which I think one way sometimes makes sense, especially if you have these coefficients as the weight on the edges, but the other way may not. So I mean, is there, I think there are these specific GNNs for bipartite graphs. Have you tried to use them instead of the regular GNN so that you don't have these issues with the making all the nodes look the same? I mean, because then you can have 2 types of nodes.
Possible. We haven't
Yeah,
tried. Right now we have 2 layers of graph sage, but we didn't do an ablation on different GNNs or.
So there are some that you can basically do. We wouldn't need to do these.
Yeah, maybe I can keep the nodes, the variables as variable nodes, and
Right.
possible. We haven't looked into that. Yeah, we haven't
And
looked
there's
into
also the weights, which way it makes sense. And the same for the encoder, the code book. I mean, VAEs, this variational autoencoders kind of do that.
Yeah.
The regularization. So I mean, something to, I don't know how, I mean, your embedding seems to be already good, so.
Yeah,
Is what
I'm not sure if this is the only setup would have worked. I would think it's not. Like, you could get something out of it. The trick, I think that the key point is the fact that you now have a vocabulary for optimization, which you didn't have before. How do you really embed that? Maybe that needs a bit of more extensive study. And the fact that you have this now nice reconstruction that does not depend on the solvers. That is really what's the key.
I'm saying, like,
Yeah.
since you're embedding, you're pretty happy with them already.
Yeah.
I mean, so I don't know these extra things would help or not, but.
Same here. I do not know, and I would be surprised that there is no other combination that will work as good, because we specifically didn't want it to really go into the nitty-gritty details of like finding the right one, something about it that gets the best. The NMI was 84%. I'm sure if you play around, you can make it a bit better, but that's not what I'm trying to achieve. But that's why there's a lot of work to be done, and I think these are great suggestions we'll keep in mind. Thank you for the new directions.
Other questions? I have a question.
Yeah.
So you said that the 3.5 million, where are those parameters? Because, in the GNN, the parameters are shared for all the nodes in the bipartite graph, right? So all the vertices and constraints for each one to basically, once you have the vector, 10-digit vector, whatever, d-dimensional, to map it to a code book, you apply that same transformation to all of them, right?
Right.
So it's a GNN with shared parameters across the node.
Correct, correct. So the two graph stage layers, so that's, you know, that you might have more or less layers, and also there's the decoders at the end.
But the test time, you don't lose decoding. So at inference time, it's much fewer parameters you need to go through.
That's correct. That's
So
correct.
actually
Inference is
answer-
really fast, by the
Yeah.
way.
So
Like
I
you can
think-
run this on, you train on GPUs, but you can run this on CPUs. Like it's, the inference is really,
I think it's an important point to make, that the forward pass is like much.
That's
more
correct.
parameters and it's going really fast.
that's correct. Yeah. The nice thing about it is that we can actually run this on CPU, which I really like because the solvers are on CPU and you don't want to go back and forth between the two.
Because NLP models, when they say whatever million parameters, you have the same parameters at the forward path as well.
That is correct. I should have mentioned. That's a great point. Thank you. I think that makes it even more interesting in terms of integration because you don't have that complexity anymore at runtime. Maybe you can use this inside the branch and bound tree, which in production environments is not being done at the moment. So maybe there's a chance that this could be the way.
Any other last questions? Well, let's thank the speaker
All
one
right.
more time.
Thank you very much for your time.